Hello students. Hello and welcome to this video. In this video, we will solve question number 121 to 130 of binomial theorems and expansions. Now, the link to download the PDF will be in description given below. As well as at the end, I will show you how you can download the PDF from the website and maintain an updated copy. I will also show you my question answer website, which I have prepared for you, so that you can ask questions over there. So without further ado, let's get started. Question 121 says that find the fractional part of 2 to the power 4n upon 15. 2 to the power 4n can be written as 16 to the power n, which can be written as 1 plus 15 to the power n. 15 will remain in denominator. Now we expand 1 plus 15 to the power n. We get 1 plus c1 times 15 plus c2 times 15 square. This c1 means 15c1 and c2 means 15c2 and so on. So obviously you see that starting from second term onwards, there will be a factor of 15. So 15 will cancel out giving numbers. So clearly the fractional part would be 1 upon 15. Question 122 says that show that the integer just above the square root of 3 plus 1 to the whole to the power 2n is divisible by 2 to the power n plus 1 for all n in set of natural numbers. We let root 3 plus 1 whole to the power 2n is equal to p plus f, where p is the integral part and f lies between 0 and 1, that is, it is the fractional part. Now, square root of 3 plus 1 to the power 2n can be written as square root of 3 plus 1 whole square to the power n, which is equal to 4 plus 2 root 3 to the power n, which is equal to 2 to the power n times 2 plus root 3 to the power n. Now, p plus f will be 2 to the power n times 2 plus root 3 to the power n. We also see that root 3 minus 1 lies between 0 and 1. So, square root of 3 minus 1 to the power 2n will lie between 0 and 1. So, f1 we assume to be square root of 3 minus 1 to the power 2n, and you square it, then you will get 3 plus 1 minus 2 root 3. So, we take out 2 outside, it becomes 2 to the power n times 2 minus square root of 3 to the power n. So, we add p plus f with f. So what we get is 2 to the power n times 2 to the power n times 2 times 2 to the power n plus c2 into 2 to the power n square root of 3 square and so on, which is equal to 2 to the power n plus 1 into an integer. Okay. Now this will be an integer. Now f plus f1 will be even number minus p is equal to an integer. We see that 0 plus f1 will be between 0 and 2. So f plus f1 is 1. And hence integer just above a square root of 3 plus 1 to the power 2n, that is t plus 1 is divisible by 2 to the power n plus 1. Now we move on to question 123. Let r is equal to 5 root 5 plus 11 to the power 2n plus 1 and f is equal to r minus greatest integral value of r, then prove that rf is equal to 4 to the power 2n plus 1. Clearly f will lie between 0 and 1, and r is given as 5 root 5 plus 11 to the power 2n plus 1. Now we take f dash is 5 plus root 5 minus 11 to the power 2n plus 1. Now clearly 5 root 5 minus 11 lies between 0 and 1. How this lies between 0 and 1 is you multiply it with 5 root 5 plus 11. So what will you get? You will get 5 5 are 25, 5 are 125 minus 121, that is 4 in the numerator, and denominator would be 5 root 5 plus 11. So clearly it lies between 0 and 1. So we raise it to the power 2n plus 1, which will also lie between 0 and 1. Now we compute r minus f, which is equal to 2 times 2n plus 1 c1 5 root 5 to the power 2n plus 2n plus 1 c3 5 root 5 to the power 2n minus 2 times 11 to the power 3 and so on, which will be an even number. So f minus f dash is an even number minus greatest integer of r, which is an integer. but f minus f dash will lie between -1 and 1. So f minus f dash is 0, or f is equal to f dash. So r f dash is equal to 5 root 5 plus 11 to the power 2n times 5 root 5 minus 11 to the power 2n is equal to 4 to the power 2n plus 1, which is equal to Rf. Question 124 says that show that 101 to the power 50 is greater than 100 to the power 50 plus 99 to the power 50. 101 to the power 50 minus 99 to the power 50 is equal to 100 plus 1 to the power 50 minus 100 minus 1 to the power 50, which is equal to 2 times 50c1 times 100 to the power 49 plus 50c3 100 to the power 47 and so on. So we take 100 to the power 50 outside, and what we get inside is 2 times 50c3 100 to the power 47 plus, no, we don't take common, we just have 100 to the power 50 here, okay, and this will be inside the bracket. So clearly we see that 100 power 50, 101 to power 50 minus 99 to power 50 is greater than 100 to power 50, and thus we have our result. Question number 125 says that find the sum of the series sigma r is equal to 0 to n minus 1 to the power r NCR times 1 upon 2 to the power r plus 3 to the power r upon 2 to the power 2r plus 7 to the power r upon 2 to the power 3r up to m terms. So we can write 1 upon sigma CR r is equal to 0 to n. The first term we take 1 upon 2 to the power r, which is equal to 1 minus 1 upon 2 to the power r, that is 1 upon 2 to the power m. Now T2 is sigma r is equal to 0 to n, CR is equal to 3 upon 4 to the power r, that is 1 minus 3 to the power 4 to the power r is equal to 1 upon 2 to the power 3n and so on. Therefore, required sum is 1 upon 2 to the power n plus 1 upon 2 to the power 2n and so on up to 1 plus 2 to the power mn, which is a geometric progression. And upon summing this for n terms, we have 1 minus 1 upon 2 to the power mn upon 2 to the power n minus 1. Question 126 says that find the last digit of the number 32 to the power 32. So we write this as 2 plus 3 times 10 to the power 32, that is 2 to the power 32 plus 10k. Therefore, last digit in 32 is same as the last digit in 2 to the power 32. Now 2 to the power 32 can be written as 2 to the power 5 to the power 6 times 2 square, that is 32 to the power 6 times 4, which is equal to 2 plus 10 to the power 6 times 4, or 4 times 2 to the power 6 plus 10r. Therefore, last digit in 2 to the power 32 is same as last digit in 4 times 2 to the power 6, which is equal to last digit in 16, or the last digit is 6. Question 127 says that prove that sigma r is equal to 0 to k minus 3 to the power r minus 1, 3n c2n minus 1 is equal to 0, where k is equal to 3n upon 2 and n is a positive even number. So we let n is equal to 2n and m is in the set of positive integers, then k is equal to 3n. Because k was given 3n upon 2, so k is equal to 3n actually, it should be n. Now left hand side we expand, it becomes r is equal to 1 to 3m. Okay, 0 will give the negative power here, so it should be 1. Minus 3 to the power r minus 1. 6m c2r minus 1. So 3n is now 6m and 2n minus 1 is actually 2r minus 1. This should be 2r minus 1. It is incorrectly written. So this should be 1 and this should be 2r minus 1. Now we expand this, we get 6m c1 minus 6m c3 into 3 plus 6m c5 into 3 to the power 3 square and so on. Now we take 1 upon root 3 outside. Okay, let me think a bit. There seems to be some mistake. So we put r is equal to 1, we get 1, and 3 to minus 3 to the power 0. We put r is equal to 2, So 2r minus 1, no, this is correct. Now we take out 1 upon root, we multiply and divide by root 3. So we get 6mc1 root 3 minus 6mc root 3 cube plus 6mc5 root 3 to the power 5 and so on. We observe that minus 1 to the power 3m minus 1 is equal to I to the power 6m minus 2. We write minus 1 as I square. Now this we can write as minus I into I to the power 6m minus 1. The I is the imaginary number iota. So we see that 1 plus square root of 3i to the power 6m is equal to 1 plus 6m c1 root 3i plus 6m c2 root 3i square and so on. So this becomes 1 minus 6m c2 into 3 plus 6m c4 into 3 square and so on plus I into 6m c1 root 3 minus 6m c3 root 3 cube and so on. Hence 1 plus root 3i, but we know that 1 plus root 3i to the power 6m is equal to 2 cos pi by 3 plus I sin pi by 3 to the power 6m, which is equal to 2 to the power 6m. Hence, equating quotient of imaginary part gives us 6m c1 square root of 3 minus 6m c3 square root of 3 cube and so on is equal to 0 because there is no imaginary part here. It's a bit involving question, but moderately difficult question it is. If T0, T1, T2, T3 be the terms of the expansion a plus x to the power n, prove that T0 minus T2 plus T4 minus and so on squared plus T1 minus T3 plus T5 minus and so on squared is equal to a squared plus x squared to the power n. So we are given that a plus x to the power n is equal to a to the power n plus nc1 a to the power n minus 1 plus nc2 a to the power n minus 2 x square and so on up to x to the power n. So T0 is a to the power n, T1 is equal to nc1 a to the power n minus 1 into x, T2 is equal to nc2 a to the power n minus 2 into x square. Now we replace x with ix. So our equation is now split into two parts. One is of real numbers and another is of imaginary part. So real part becomes a to the power n minus nc2 a to the power n minus 2x square and so on. And imaginary parts contains the odd numbers nc1 a to the power n minus 1x minus nc3 a to the power n minus 3x cubed and so on. Now this is equal to T0 minus T2 plus T4 so on. Imaginary part is T1, T3, T5 and so on. To take the modulus and square, we get the desired result here. Now question 1, now there are certain questions based on a statement. If 1 plus x square to the power n is equal to a0 plus a1x plus a2x and so on up to an to x to the power 2n, then we have to show that question 1 and 129 a0 plus a1 plus a2 up to a2n is equal to 3 to the power n. So this is very straightforward. You put x is equal to 1, it becomes 3 to the power n, and we have a0 plus a1 plus a2 and so on. Question 130 says that a0 minus a1 plus a2 and minus and so on up to plus a to the power 2n is equal to 1. So here you put x is equal to minus 1. So this will become 1. If you put x is equal to 1, this becomes 1 to the power n here. So it will be 1 here. And if you put x is equal to minus 1 here, then it becomes a0 minus a1 plus a2 minus a3 plus a4 and so on. So that's how we solve question 129 and 130. And with this, we come to the end of 130 problems. And now I'll show you my website, ashtavakra.org. So second, third, and fourth link are algebra, trigonometry, and coordinate geometry. When you download the PDF, it won't have date. So you add this date to your download PDF and come back after some time, say 15 or 30 days. And if you see the date has changed, then you download again and add the date again. Now I cannot add the date because that will make the entire earlier links invalid. So it is practically not feasible. Also, if you want to ask questions, you click the eighth link and you will come to Umjika and you can make a login here and ask questions. There are tags already created for you: algebra, calculus, coordinate geometry, geometry, mathematics, trigonometry. These tags you can use. and ask questions to me related to class 12 maths, which is your course. So with this, I will end this video here, and we will meet again tomorrow with 10 more problems on binomial theorems. So thanks a lot for watching the video, and have a great day. Enjoy and keep learning. Thank you.